Hello everyone, welcome to this tutorial. My name is Emerson Ahari. I'm a Google Earth Engine developer. In this tutorial, I'm gonna show you how to calculate dust risk map in the Earth Engine platform and Python API programming using machine learning technique and by integration of climatological data and dust related parameters. So, at the end of this tutorial, you will be able to produce such kind of map for your region of interest that's showing the probability of the dust events or the dust storm across your region of interest. The higher values, higher probability or higher risk, and lower values, vice versa. So this map is really useful, giving us some sort of insight about the regions might be affected by the dust events before it happens in the region of interest. So now I'm gonna show you how to do this in this tutorial. Okay, let's make a new notebook in the Colab environment. In the first step, I need to import or install the essential libraries we need to work with Earth Engine platform. Let's start with XEE library. So, as it is not built-in available here, I need to upgrade it, the library, XEE library. The previous tutorial completely addressed about the XEE library, but if you still need to know more about the XEE, just go to the browser and start searching about Google Earth Engine with XEE. So you will find a GitHub page, a detailed instruction about how to use this library. Here you can find the most recent instruction about how to deal with the XEE. So accordingly, I'm following the instruction and installing the upgraded version. So the next step, I need to install GEE map, but it is better to install the upgraded version, UGEE map. Let's run it once again. Now I'm waiting for these libraries to be installed. Then clear the output and import the EE library, Earth Engine library. The EE helped me to establish a connection between Colab and Earth Engine. EE authentication first and initialize the Earth Engine account. The account project ID, how we can find it? Go to Earth Engine code editor environment, code.earthengine.google.com. There you can find the Earth Engine main editor. In the upper right, you can see your account information. Drop it down, go to project info. Here you can find yours cloud project. Just paste it like this. The another argument here, OPTURL, the Earth Engine server address. Go back to the GitHub XEE GitHub page. There you can find the server address, the OPTURL. Select and paste. Let's run the cell, and now Google asking us permission to get access to the Earth Engine account. Select your Earth Engine account, click on continue, and continue again. Okay, after 21 seconds, you can see the account initialized successfully and the account installed successfully and without any challenge. meaning that from now on I can use Earth Engine catalog functions and resources under Python programming standard. So, before going further, I need to select the region of interest. The GEE map, the library already updated, is a kind of library developed to offer additional resources to the Earth Engine under Python language. So here I need to call the region of interest or select the region of interest by map function from GEE map. Let's run the map. And also here the Gemini assistant is available in the right side. You can remove it or you can call it through a toggle available here. So it's a good to actually solve the problems or fix the issues you may face in the programming. So here we have a user interface with the drawing tools, easily allowing us to select the region of interest. As an Iranian, I'm interested to find the regions exposed to the dust risk in my own countries in Iran. So using the rectangle tool available here, I select my own country, Iran, is like this. So the next step, the ROI, I need to have this area as a variable. From the map, select the last feature, draw last map, draw last feature, just like that. Convert it to geometry. Let's run. I have a polygon with 5 vertices. As you can see, the polygon explaining by the coordinates available here. So the ROI created. Now I need to call the climatological data and dust related data for this region of interest. So now I can use Earth Engine datasets. So make a new browser, open a new tab in your browser and search about Google Earth Engine MODIS AUD datasets. So here you can find the dataset tagged AOD in the Earth Engine. There are 2 options. One of them is land surface, BRF, and the other one is Terra Aqua Mayak Land Aerosol Optical Depths, daily 1 kilometer. It's not daily, it's more like hourly data sets. But anyway, click on this and you can see this is available over the last 25 years and 1 kilometer resolution. So I can call this dataset by the collection snippet. Make a new variable. The new variable is AOD. Paste the collection snippet and define a filter date. So I need a time start and time end. I want to choose one single year to calculate the dust risk map. So let's define a time start and a time end. For example, the target year is 2020. Time end EE date 2021. Just like this. Now filter your data based on from time start to time end. There are various bands here. The optical depth 55 is the target band. The higher wavelengths compared to the first one are preferred for non-urban areas. If you focused on urban areas, the shorter wavelengths suggested. So That's why I'm selecting the bigger or longer wavelengths. Or we can change its name while we are selecting. For example, the existing name is the optical depth, but the new name I need is simpler and shorter. So, select AOD. The AOD band is selected. So, then I need to print the result to see how it works. So limit, for example, let's call the first 10 image to make sure everything's fine so far. Drop it down and here you can see a list of features. Everyone AOD selected, all of them available here. And also there are some properties that should be considered in the analysis. For example, here we have a satellite option. This product is a combined product between Modis Terra and Modis Aqua. So, for example, I prefer the Aqua. So, let's define a new filter like this. Earth engine.filter.eq. So the filter is about the satellite property. The satellite property should be A. So now I'm calling those AUD dataset belongs to Aqua or Terra. It is Aqua, T is Terra. So there you go. Let's run it again. And now you can see all of the existing dataset belongs to the Terra. So, and it is important to filter our datasets based on the region of interest as well. So that filter bounds based on ROI. So that's much better now. So now I need to know how many images available for 2020. So here just I need to calculate the size, then get info returns the result here. I'm waiting to see how many datasets available under AOD variable. So because this is hourly dataset and you can see over 18,000 image available for only 1 year because it's hourly dataset. So now I need to convert it into monthly average because I need to do the risk mapping for every month and aggregate them over through the temporal dimension. So to do this, we need to define a function to convert the hourly data into monthly format. So the time start and time end already defined. So we need to calculate their differences from time end to time start based on number of months. So round it and make a list starting from start to end with monthly interval. Time list earth engine dot list dot sequence. So starting from 0 to the number calculated by time difference. Okay, make a loop structure now. So I need define a function by lambda. Each number in the time list consider it as x, and the list will be updated based on time start going forward based on X interval and month format. Okay, let's print the time list. So as you can see, now we have a list starting from January 2020 to January 2021, but January 21 should be excluded. That's why we subtract by 1, because the list is starting from 0. So as you can see, the issue fixed. Okay, now I have a list of monthly frequency. Now I can make a filter or define a monthly filter for the AOD dataset and aggregate them into monthly average as well. So to do this, we need a function, define monthly function. Two arguments considered in this function. First is the date and the next is the collection. The input to the function is the time list. So define start date ee.date from date, because when the list imported into the function, the first row considered as start date, just like this, and end date equals to start day going forward by 1 month. So this is the end date as well. And now img collection, get the collection data like AOD, filter it based on start and end of each month, and aggregate by average over the time. The function return call image, but to avoid any problem, let's define the call size as well. Get the call image, get the number of the bands by size, convert it into a number, ee.number, just like this. This is helpful because if we have any gap for each month, we can exclude or skip that image by the size of the collection. So the output, the average image, will have new properties like new system time start, set to a start date with millisecond format, and the next property will be band or band size set to call size. Okay, now function is created and we need to apply on AOD datasets. A new variable, monthly AOD, created. Define an image collection format because the input is a time list, but we need to return an image collection. Call the time list, make a loop structure to apply the monthly function on each row, because we have multiple rows and we need a loop to get the start date from each row separately. So lambda x, each date considered as date. Monthly function has two inputs. The date is x and collection is AOD here. So, and let's call monthly AOD. Definitely takes a bit time because 18,000 satellite images are under processing. So as you can see, AOD converted into a monthly format without any challenge. Okay, the monthly AOD dataset is ready, and we need to repeat this process for climatological data that's directly or indirectly associated with dust events. Parameters like soil moisture, precipitation, temperature, and for example, or parameters like vegetation cover, all or wind speed, all of them somehow correlated or associated with the dust event frequency. So now in the next step, I need to call the climatological and environmental data before dive into the modeling process, because regarding to the modeling, we need to prepare the data set in a standard way and then use that data set or prepared data in the modeling structure and see how much results are accurate or which areas affected by the dust events. So now the best option, I think, in this time is the TerraClimate datasets with a good spatial resolution. Go to Google Earth Engine, TerraClimate datasets. Here you can find the TerraClimate, the monthly dataset offering climatological parameters like, for example, evapotranspiration, precipitation, runoff, soil moisture, temperature, and on it goes. This dataset available with monthly frequency, and we can use it in our study. It has 5 km resolution, and easily we can use this to make a high resolution map. So now let's call the Terra variable as well. Terra dataset created. So there is an Earth Engine snippet here. Let's copy and paste like this. Define a filter date starting from time start to the time end. And here we will have, for example, a couple of bands that should be considered in this study. Parameters like, for example, precipitation, soil moisture, and temperature. Precipitation, soil moisture, and wind speed, for example, and also maximum and minimum temperature in amount, T temperature, minimum temperature, and maximum temperature. Here you can see both of them are available, and these are temperature data sets. Yes, these are good parameters for the from the TerraClimate side with monthly frequency. There are some scale factors, but we don't need to convert them into a main range of values because we have focused on modeling in this study, and we don't need to focus on the range of the values. So now I need to make a print to make sure everything's fine about TerraClimate datasets. There are 12 elements as well here, and here you can see we have 5 bands for each month, including precipitation, soil moisture, wind speed, minimum and maximum temperature, all of them available. But remember that to avoid any problem, it is better to repeat the monthly format for this dataset as well. It's true that this is already monthly, it has already monthly frequency, but we have to redo the monthly conversion again to make a similar structure with AOD monthly dataset. Let's make another variable, Terra monthly, like this, and make an image collection format. It's same as the previous example. call the time list, make a map, define a function, each input considered as x in the time list, and apply the monthly on x and the Terra dataset. Let's call the Terra monthly again to make sure everything's fine. So the Terra monthly again returning 12 elements, but this time everything including the system time star is completely matched with the AOD monthly frequency datasets. So the vegetation still is missing here, and NDVI is well representing the amount of the vegetation cover in the study area, because the higher vegetation here, for example, showing lower dust storm, and also the vice versa. So make another tab in your browser and search about Google Earth Engine, MODIS NDVI 16 days frequency product. So MODIS combined 16 days NDVI is available here. You can go, and also you will see that it has 60-day NDVI, yes, and available from 2000 to 2023, and only one single band is the NDVI. And also there are other indices as well with this title. For example, the other indices available with 250 meter resolution, but the resolution doesn't matter here because the target resolution is around 5 or 10 kilometer, but we will resample it at the end. So anyway, here the vegetation indices 60-day global 250 meter resolution is available through the collection snippet. Easily you can call it same as the previous examples. The Terra climate, now we will have a new variable in the NDVI and define a filter date starting from time start to time end. The target band here is NDVI, and no need to apply the scale factor here, just we need to convert it into a monthly average. So NDVI monthly, let's convert its name from capital format to a small letter like this, NDVI. Yes, NDVI monthly sets to define an image collection format again, call the time list, make a map, define a function, apply the monthly format on dates and NDVI. Finally, let's print the monthly NDVI. Again, 12 elements available here. In each date we have one band that is NDVI. So the predictors NDVI climatological data are available and existing here. Just I need to incorporate them into a single data set with the original data set that is AOD monthly. So make a new variable collection, and the collection sets to get the monthly AOD combined with Terra monthly and combined with NDVI monthly, just like this. Let's call the collection. After a few moments, you can see still we have the same collection with 12 elements, but we have all the bands for corresponding date for the same dates available. AOD original and the predictors, all of them for each month, prepared, stacked next to each other. So And in the next step, I need to convert this dataset from image collection formats into X-array structure. That's why XEE library is already called in this code. So, but the XEE incorporated with X-array structure. That's why we need XEE and X-array next to each other in the code structure. So the dataset sets to from X-array call open dataset just like this. The input dataset is a collection based on Earth Engine protocol define a coordinate system EPSG 4326. This is WGS84 unique ID. And the geometry region of interest is the ROI, and a scale is about, for example, now I need to set a pixel size for the output. We have a multi-resolution collection here, AOD 1 kilometer, Terra dataset 5 kilometer. The monthly NDVI is, for example, 250 meter. I prefer a 10 kilometer as a target resolution here because I'm working in a national scale and the study area is really big. That's why a bigger pixel size easily manageable in the next step. If you want to work on a very small area, I'm suggesting 5 kilometer resolution. But because of the extent of the region, I prefer 10 kilometer. The scale size is based on a degree here. 1 means 100 kilometer, zero point 0.1 is 10 kilometer. Let's run the dataset. Code is running and converting an image collection into an X-array format. The X-array format has such kind of a structure, a multi-dimensional array structure, where you have each dimension, spatial and temporal dimensions separately with the array format, and we have a couple of variables instead of the bands. So now I need to do some sort of visualization to see what do we have here. So let's sort the data sets through the temporal dimension first, like this. Sort by over temporal dimension, because it's very important to sort the data set. Sometimes the data actually uh, faced with the disorder issue over the temporal dimension over this kind of conversion. So now I'm applying also a simple scale factor like 1 just to make sure I'm creating a new dataset apart from the original one. Let's run a code. This multiplication ensures the higher speed of processing in the next step. There is no scientific reason, but this simple equation help us to increase the efficiency of computations in the next step. Maybe this part taking a little bit more, but no worries. After this step, the speed of processing highly increases. So, and I tried to explain everything in the most efficient way I learned so far. So if you faced with any challenge in this tutorial, you can find the code example below this video on my YouTube channel. So, or you can put your comments there. I will look at them as soon as possible and answer. So, it's still under computation. After computations done, I want to show you or give you a preview about what we have prepared from AOD, from precipitation, from NDVI to understand what's going on in the region of interest as well. As you can see here, it's done over 1 minute. The dataset didn't change, and also we have a same dataset with the higher speed of processing. Let's select a variable like AOD here and define a plot. X-axis in the plot sets to the longitude dimension. Y-axis sets to latitude dimension. As it is a multi-temporal dataset, the call sets to the time to show a multiple frame. Each frame belongs to a single year, a single month. Robust sets to true, increases the contrast, and call wrap shows, for example, 6 map per row. Let's run and see how the study area looks like in the AOD view. From the AOD view, you can see the area mostly affecting by the dust events. The higher AOD values showing higher RSL and vice versa. Or we have NDVI as well. This is also the NDVI layer. We have also the precipitation layer. You can see we have lack of precipitation over the Persian Gulf and Oman Sea. So, or we have, for example, the wind speed values like this. So, as some of the pixels missing over the water body, so it is better to exclude the water from the processing to avoid any problem in the calculations. So how to do this? We can use MODIS land cover datasets. Open a new tab in your browser and let's search about Google Earth Engine MODIS land cover datasets. MODIS land cover yearly global 500-meter resolution is available. So here through the Earth Engine snippet, you can call this dataset as well. So I need to make a mask using land cover datasets. For a period of time I'm working on dot filter date from time start to time end. Different land cover layers available in this product. The LC type 1 is the most common product users typically utilized in their studies. So, and I need to find the most frequent classes over the last 25 years to ensure that I have a single land cover that's used for this study area and that to use to separate the water and non-water pixels. So the mode find the most frequent classes in this regard. So in the LC type 1, we have a table of contents showing class number 17 equals to the water body or associated to the water body. So the equal 17 selected the water body and not convert it into a 0 value. I want to have 0 values for the water body and 1 value for the rest of the classes, like a mask structure. So let's run and let me convert it to a water mask, the layer name. I need to make another array structure for the mask dataset as well. ds mask sets to, again, from xr open dataset. The input data is mask under Earth Engine Protocol and CRS EPSG 4326. Same coordinate system, same study area, ROI, and same pixel size. So the DS mask, let's run. Here you can see one variable and also longitude and latitude. As we have no temporal information here, we need to get rid of the time as well. Let's squeeze the time, squeeze the time or temporal dimension. You can see time is gone, but still it is in the coordinates. So I can drop the time variable like this. Okay, the dataset is prepared. ds mask sets to this process and simply multiply to 1 to increase the speed of processing in the next step. Okay, the ds mask is ready. Let's visualize the ds mask. The variable name is water mask plot with x and y, longitude and latitude. So now we have a binary layer 0 and 1, labeling water as 0 and non-water as 1. So here I can easily apply it on this data set. How? It's really easy. Let's import numpy as np. So now the ds again gonna be updated based on the land cover to exclude the water body using the xr called the var function. Now I need to make a new xarray dataset in which every var in the ds mask sets to, for example, 0, replace by np.nan, and the rest of the pixel will have the values available in the ds dataset. Let's run. So something's wrong here. There is a mismatching. So ds mask dot water mask. Now the problem is fixed. So let's call the vs again, and now you can see the water bodies excluded. What about the, for example, wind? This is the wind speed. What about the precipitation? This is also true. What about the soil moisture? Excluded as well. And also in the AOD, even the water body excluded. Okay, now we are focused on the land dust, all the dust events happening over the land. So in the next step, I need to define a 0, 1 or a binary dust layer using the AOD datasets. In the AOD dataset, the AOD should be actually returned to a normal range of values. If you back to the AOD dataset here, in the Earth engine, you will find an scale factor 001. After applying the scale factor, the range of values in the AOD will be between 0 and 1, 2, or 3. So the the values greater than 0.5 or zero point 0.6 associated with the dust event. So now I need to apply the scale factor first and then select the pixels greater than zero point 0.5 or zero point 0.6 to make a binary dust map. Let's do it. So in the existing data set, I'm gonna add a new variable, dust variable, sets to. So from the DS, select the AOD band, apply the scale factor like this, put them into a tuple structure, and then select pixels, select the pixels after applying the scale. Then I need to select pixels greater equal than 0.5 dot as type integer. Want to make sure it has an integer structure. Let's run. Print the data set. You have a new data set, a new variable that is dust, that separated the dust events or dusty areas and non-dusty areas. Let's visualize it. ds.dust, make a plot, x longitude, y latitude, call time, call wrap. Here is, for example, 6. Let's run. Now we have a binary layer that shows the dusty areas by 1 and clear areas by 0. So now I need to use this binary layer to make a dust risk probability map based on association between this layer and the rest of environmental parameters using logistic regression. So the dataset is ready now for the modeling process. Okay, now I need convert the dataset into a data frame structure or a table. So call here I will have a data frame where get the dataset, convert it into data frame, just like this. Let's call the df. So now as you can see here in the table structure, I have longitude, latitude, and time. Why this conversion is important? Because in the table format, I can use all Python resources for my dataset. And finally, I can return my dataset back into original format as well. So remember to drop the no data values. We have some no data across the water bodies. So now the no data also removed for this for the sake of the modeling. So now I need to separate the data set for training, testing, and etc. From sklearn dot model selection, import a function that is train test split function. So we need to define the predictors and the original value. Original variable is the original variable shows by y sets to from data frame select the dust like this. This is a binary layer. In the logistic regression, it is important to have a binary layer as the original variable. X sets to all environmental predictors like NDVI, precipitation, soil moisture, wind speed, and maximum and minimum temperature. TMMN, minimum temperature, TMMX, maximum temperature. All the predictors selected. You don't use the AOD as a predictor because the AOD directly associated with dust and cause a problem in the processing step. So now I need to separate the train and test values using sklearn. Xtrain, Xtest, Ytrain, and Ytest sets to call the function train test split x and y. Test size sets to 20% of data considered for the accuracy assessment, and I need to select the data sets or values randomly. The random state should be 42. Okay, the data sets prepared for the modeling. Now I need to call the model from sklearn.linear model import logistic regressor. Import logistic regression. Like this. Okay. Model sets to logistic regressor with maximum iteration sets to 1000 times. Then the model should be fitted to the train datasets Xtrain and Ytrain. Let's run the model. Now the model is trained and I can use the model to predict the predict and calculate the probability for the original variable that is dust here, a binary layer. Okay, predicted y sets to the model predict based on x test values and y probability also sets to get the model predict the probability based on x test. Let me check the previous code to make sure everything's fine. Yes, both calculating based on x test. So just like this. Let's run the prediction. Okay, now I have predicted for the test data associated y probability and predicted values. Now I need to do the accuracy assessment using existing metrics from sklearn.metrics import classification report, and the other one I think is, yes, there it is, ROCAUC score. This is another score, another statistical metric that we use to estimate how much classes close or separated, and classification report shows how much predicted values correspond to the real values. So, okay, but probability is important here, but we can also check the prediction accuracy by the classification report. So, class reports. As you know, we have two classes here because the the dust map shows 0 and 1. Here we have two classes, 0 and 1. The majority of area labeled as 0 and just minor areas considered as 1 here. So, as we have two classes, the report including only two values called the classification report for y test and predicted values. Print class report here. So now you can see the overall accuracy showing here. That is not a good measure for the accuracy assessment, or the class accuracy also highlighted here. We have two classes, 0 and 1. 0 is a major area, 1 is a dusty area. So you can see the accuracy is around 45%. The accuracy is not very high because all the values is very low. But it doesn't matter because the majority of classes, the majority of area covered by 0 values, and the classification or predicted values is not our target here. Just it is important how much the classes 0 and 1 well separated from each other, which can be assessed by a second score here. As you can see in the previous example also, I showed how to do this. In the previous example also, I had a small value for in the prediction result, but the probability is much better. So now the next is probability accuracy, or probability. Here it is ROC should be better, a variable name. So ROC AUC score like this between y test and y probability values should be in one dimension format. That's why I add this sign. I add it like this. Print ROC. The ROC ranges between 0 and 1. The values close to 1 shows the probability well discriminates the 0 and 1 from each other. So our classes well separated in the probability calculation. So that's very fine, and you can see the value is highly close to 1. Okay, so now I can apply the model on all predictors in the dataset to convert it into an image and show which areas experience exposing more to the dust risk. So we had a data frame like this. I need to add a new column or a new variable that is risk. Sets to call the model. From the model, I need to predict the probability for proba. Should be like this, based on predictors including NDVI, precipitation, soil moisture, and also with one dimensional structure. I'm converting this data from 2 dimension into 1 dimension by this sign. Let's run. Okay, the risk values calculated here. Bigger values meaning higher risk and vice versa. But it is in data frame structure and I need it into an X-array format. It is easily manageable. Call the df and convert it into an X-array format, just like this, and sort it by temporal and spatial dimension, time, latitude, and longitude, called the dfx. So now you can see the risk variable is available as a separate variable. So let's visualize the risk values for each month separately. Dot plot x sets to longitude, y sets to latitude, call sets to time, call wrap sets to 6 for example, and robust should be true. Let's run a code, and here you can see the probability map. The yellowish area showing the higher probability and a darker area lower probability of dust about the dust events. We can also increase the size of the values by some scaling technique. For example, we can for example here I can multiply values to 100 or 1000 to have a bigger values for the interpretation. That's a little bit easier for the analysis. For example, here I'm calling the dfx, select the risk variable, multiply to 100 for example, and I need to calculate its average over temporal dimension. So because I need one single risk map to show which area is affecting more or less. So this is a risk layer, get the risk layer and make a plot. X longitude, Y latitude, no need call because we have only one single image. Robust is true. Let's run. Here you can see even we can increase the scale factor values. You can see the yellowish areas actually over 40% exposed to the dust risk event and vice versa. So here it is easier to understand. For example, the yellowish areas more risk and also the bluish area lower risk about the dust events. This layer created by incorporated modeling between climatological data and the dust datasets. I hope you like it as much as I did. Please share this tutorial with other remote sensing fans in all around the world. You can find several Earth Engine related studies and example on my YouTube channel. Thank you for your attention.